Hello everyone, I am Revathi. I am working as an assistant professor in SNS College of Technology in Department of Artificial Intelligence and Data Science. In the last session, we completed the define phase of our design thinking approach where we clearly stated our problem. How might we design our data structure that allows fast searching and range-based queries without scanning millions of records? Today we move to the next stage, Ideate phase. Let's imagine we are database engineers working for that bookstore that couldn't find its book quickly. We will start thinking, what are the possible data structure we could use to solve this problem? How can we design one that supports both quick searches and fast range queries? As you watch, try to think along with me, which structure would you access if you were designing the bookstore's database? Let's think of possible solutions. First idea is sequential search. The simplest approach is to check one record after another. This works for small data, but when we have thousands or millions of records, it becomes painfully slow. So sequential search is not practical for large databases. Second idea is a binary search tree. Next, we might think of using a binary search tree. It is better because we can divide and conquer of the data each time. But as data grows and updates happen, the tree can become unbalanced, increasing the height and slowing down the search. So we need something more suitable. Then comes hashing. Hash tables give instant access for extract matches like finding a book by its unique ISBN number. But they fail when we need range queries like finding all books priced between 300 and 600 rupees. Hashing breaks the sequence of data so range searches are inefficient. Now we come to the B tree. It solves some of these issues. It says balance, support insertions and deletions efficiently and works well for indexed search. But B trees still have a small drawback. Data can exist in both internal and leaf node. So for sequential access, we need to traverse multiple paths, which is slower. At this point, our mind start connecting the dots. What if we could store all data only in the leaf nodes, keep the internal nodes just for indexing, and link all the leaves together for fast sequential and range-based access? That is the spark of innovation, the idea that leads to the B plus tree. The B plus tree combines the strength of the B tree with the speed of a linked list. It gives the faster search, then faster range queries and efficient data access all in one structure. This is how the Ideate phase transforms a simple problem, slow search into a smart, efficient and scalable solution. To prototype, we create a small example. We build a B plus tree with a few keys and see how data gets organized in internal and leaf nodes. We test how operations move from the root to the appropriate leaf and how the linked leaves support quick sequential traversal. Now it's time to test our prototype. We perform insertion, deletion and range queries to check if our structure maintains balance and order. The result confirmed that B plus tree provide both logarithmic access time and sequential range efficiency. Now let's do a quick group activity. Each group receives a set of keys 20, 30, 40, 50, 60 and 70. Your task is to draw a B plus tree of order 3, then perform a range query from 30 to 60. Discuss how many nodes were accessed and observe how linked leaves make range queries faster compared to unlinked structures. In a B plus tree, we perform three main operations: search, insert, and delete. The search starts at the root and follows keys down to the leaf level. Insertion ensures that nodes split only when full, maintaining balance. Deletion merges or redistribute keys to keep the tree height uniform. All of these operations happen efficiently with minimal discretes. B plus trees are not just theory. They power real systems. You will find them in database indexing in MySQL, PostgreSQL, and Oracle, file systems like NTFS and HFS, and search engines for maintaining keyword indexes. Looking forward, B plus trees continue to evolve. Some exciting innovations include adaptive B plus tree self-tune based on query patterns, encrypted B plus trees that is used for secure indexing, and distributed B plus trees for managing massive cloud-based data sets. These advancements make B plus tree highly relevant in today's data-driven world. Let's apply this knowledge with a case study. Imagine a hospital database storing patient records, treatments, and billing details. Doctors often query patients by ID or range of dates. Without indexing, these queries takes too long. By implementing B plus tree index on patient IDs or admission dates, the hospital system can search and retrieval data in milliseconds. This case study shows the real power of B plus tree. To summarize, let's recall the key points in our mind map. Structure, internal and leaf nodes with linked leaves. Advantages, fast search and range queries. Design thinking, empathy-driven solution for efficient data retrieval. Applications used across databases, file systems, and search engines. Future, adaptive, encrypted, and distributed B plus tree. B plus tree truly bridge the gap between performance and scalability. Thank you.